Podcast is going to talk about the network layer, layer 3, if we're referring to it by OSI model layers, the network layer. The network layer, as it says, layer 3. The common network layer we're going to be talking about is going to be IP, the Internet Protocol. In this case, we're going to be talking about IP version 4, which was the original version that we used until IPv6 became available. We'll talk about IPv6 later on, not today, a few weeks, but IPv4 is the network layer protocol we'll be talking about. This is where the network layer exists in the TCP IP protocol stack. The network layer will take data from the transport layer and it will pass that data down to the data link layer for delivery. The Internet Protocol, IPv4, was defined in RFC 791 in 1981. It was limited in scope to deliver an internet datagram from a source to a destination. So it will get it from here to there. That is its goal, to get it to the other machine. IP is not worried about getting it to the actual program on the other side. IP doesn't concern itself with the browser that it's going to or the web server. It just wants to get to the machine, and then the upper layer protocols will take care of delivering it to the actual process that needs it. There are no mechanisms to augment end-to-end data reliability, flow control, sequencing, or other services. IP makes its best effort to deliver the data. It does not try to figure out if the data actually made it or not. It doesn't put the data back in order. It just delivers the data. IP treats each datagram as an independent entity, unrelated to any other internet datagram. So it's going to send a chunk of data from a source to a destination. If you need to get that chunk of data reassembled in the proper order, IP is not going to do it for you. There's no idea of connections or logical circuits. Some network layer protocols would create a logical circuit before it would send its data, and then all the datagrams would go across that logical circuit in order. IP does not work that way. So IP is worried about end-to-end delivery. As we see from the slide, I have a computer on one side, I have a computer on the other side, I have a cloud in the middle. That's how most end users think about a network. It's just some stuff that does stuff. IP will get it from this computer to that computer. A more realistic view is having a bunch of routers in the middle, because that's what really exists. So IP will send your source workstation will want to send to the destination workstation, and it will send it to a router, and that router will examine it, and it will decide what to do with it, and it'll send it to the next router, and that router will examine it and decide what to do with it, and it'll send it to the next router, and it'll keep doing that until it finally gets delivered. We'll talk about how that actually happens in a few minutes. The RFC defines two basic functions for IP: addressing and fragmentation. Addressing, IP uses the addresses carried in the internet header, the IP header, to transmit internet datagrams toward their destination. I'll pause for a minute to think about that. Transmit internet datagrams toward their destinations. It doesn't say to their destinations, it says toward their destinations, right? The IP function on any particular host or router does not know the full path that a packet or datagram will need to carry to get to its destination. It just knows how it can get it one step closer. And we'll talk about that in a minute. The selection of a path for transmission is called routing. Routing is a function of the network layer. Routing occurs based on the network layer addresses. Another function of the IP protocol, as defined by the RFC, is fragmentation. Fragmentation is the breaking up of datagrams when necessary if they need to pass through a smaller network. If you'll recall from our layer 2 discussions, we had the idea of MTU. That is how much data can be carried in one layer 2 frame. So if we're sending traffic across different types of layer 2 networks, then there may come a possibility that one of the layer 2 networks that our data needs to traverse has a different and smaller MTU. And if that is the case, then our larger datagram may not be permitted to go through or cannot pass through that link without being broken up. We'll talk about that more in a few minutes. Addressing and routing IPv4 addresses have 32 bits in length. There are two parts to the address. The RFC defines that as the network number and the local address. I generally refer to it as the network portion and the host portion. The network portion is the same for all machines on the same network, and each machine will have a different host portion or local address to uniquely identify that machine on that network. How do we figure out which part is the network portion and which part is the host portion? Well, we use the subnet mask. The subnet mask consists of a bunch of ones and some zeros. Where there are ones determines the network portion, and everything else is the host. Originally, IP address scheme was defined in a classful manner. There were 5 classes: A, B, C, D, E. A, B, and C were used for hosts. D was used for multicast addresses, and E was reserved. And the default subnet mask was determined by the class of the address. So a class A had a default mask with 8 bits, which would be 255.0.0.0. A class B had a default mask of 16 bits, which was 255.255.0.0. And a class C had a default mask of 24 bits. So that'd be 255.255.255.0. So back in the day, that was the only options for sizes of a network. You have a B, or a C. That ended up not working out too well once we got to the point where more people were trying to use the internet, because we were running out of addresses because we did not have any flexibility in how we could allocate those addresses. So classless addressing was introduced in RFC 1519. Classless addressing allowed us to get away from the default masks and be able to use any length mask we want. It's also referred to as classless interdomain routing, or CIDR, as you see on the slide. And we use variable length subnet masks, or VLSM, with this idea of classless addressing. So, for example, before we could have 8, 16, or 24-bit network masks. Well, now we can have pretty much any network mask we want. We could have a 25, we have 27, we could have a 18, and we use that based on how many hosts we need in a particular network. We can manipulate our masks to give us the actual proper size network for our needs, instead of just having one giant network, because that's what the specification said. Routing, as we said earlier, the routing is trying to get the datagram towards its destination. So the process of routing is getting the datagram one step closer to where it needs to go. And we will talk about how that happens. 2 things we're going to talk about: how a host looks at routing and how a router looks at routing. Usually on your host, you have routes for any connected networks that exist on that host. So, for example, if you have more than one interface card in your host, you're going to have a connected route for 2 different networks that you're connected to. And then you usually have a default route on your host, which says, hey, if you don't know where to send this packet to, send it to the default route. If you want to look at your routing table on your host, netstat-rn will do it on Windows and Linux. It will show you your routing table. How does a host decide how to route things? Well, first it looks to see if the destination is on the same network it's on. If it is on the same network, it sends it locally at layer 2, as we talked about last week, or not last week, in the layer 2 slides. That would be direct delivery. If it is not on its local network, then it will usually send it to its router, and its router will take care of getting it the rest of the way. So the router would be one hop closer towards the destination. This host does not know exactly how to get that packet delivered, but it trusts that if it sends it to its router will take care of getting it delivered. So let's step back for a minute and talk a little bit more about how the host actually decides if it wants to send it locally or to its router. It's going to compare its IP address and its subnet mask to the destination address. And if the network portions between its IP address and subnet mask combination and the destination IP address and the subnet mask match up, in other words, if they are on the same network, then it will send it locally. If it's not on the same network, then it's going to send it to the router. So here's an example of host routing. I have 2 hosts. and I have a cloud. So assuming these networks are, this is 10.1.1.2 and 10.1.1.3, and the router is 10.1.1.1. If the PC at the bottom wants to send to 10.1.1.2, it's going to say, oh, hey, I'm connected to the 10.1.1 network. I'm going to send it directly. It'll use ARP to get the MAC address of this workstation and send the data directly to that workstation. If it wants to send traffic to 9.10.11.12, it's going to check its routing table and say, oh, 9.10.11.12, I'm not on that network. Let me send it to my gateway, which would be this router, and it's going to send the packet to, 9.10.11.12 to the router, and the router will then process it in a way which we're going to talk about in a moment. So let's pause for a moment to consider what I just said. This is important. There's a question on the midterm about how a host routes a packet. If your answer is going to your answer will have nothing to do with the router other than it is going to send it to the router. The host is going to check the destination IP address and compare it to its own IP address and subnet mask and determine if it is on the same network or a different network. If it is on the same network, it will send it locally. If it is on a different network, it will send it to its router. That's important. I've been asking that question for years now, and people don't really do that well on it, so I'm telling you it's on there, so you have no reason not to get it right. The host does not ask the router anything. So people want to say the host asked the router to send to where the other host is. Well, the host doesn't ask the router anything. The host decides on its own whether the packet is on the same network or a different network, and then sends it to the router or locally to the other machine if it thinks they're on the same network. So how does a router route? Well, I said the host is going to send it to the router. First thing the router is going to do, if you remember our discussions about layer 2, is just going to remove the layer 2 frame so it only has the IP datagram left. It's going to extract the IP datagram from that, extract the IP destination address from that datagram, and it's going to compare that datagram to some things. First, it's going to check to see if it's to that host. So if the packet is actually to the router, say you're SSHing into the router, then it's going to pass it up the protocol stack to the transport layer. That's the first option. If it is for a connected network, that is, if it's for a network that the router is connected directly to, then it's going to deliver that packet to the final destination, because the final destination should live out there on that network. And if it's for any other destination, so if it's not for the router, if it's not for a connected network, the router is going to check its routing table and send the packet on its way. What does that mean, on its way? One step closer to where it needs to go. So it's going to check its routing table. How do we see the routing table? Well, on the Cisco routers we'll be using in class, we'll use the command show IP route. Important command. We'll use it to view the routing table on the router. So here's an example. I have a little network here, and I'm showing a routing table for the router. If you look at my network, I have 172.16.100.0/24 on the left, 172.16.101.0/24 on the right. The top network shows my router being connected out to some cloud. 172.16.102.0/24 is the network out there, and then I have a routing table. So let's say we want to send a packet from a machine on the left network, the 100 network, to the 101 network. Let's talk about what's going to happen. So this PC down here is going to want to send a packet to 101.2, for example. It's going to look at its subnet mask, IP address combination, compare it to the destination, and say, oh, hey, I'm on the 172.16.100 network. This packet needs to go to the 172.16.101 network. That is different. I'm going to send it to my router. So it's going to send it to the router. The router is going to get it, take the IP datagram out of the Ethernet frame. It's going to look at the destination address and say, oh, this packet needs to go to 172.16.101.2. That's not me. Let me check my routing table. Oh, hey, I have a connected route. This was the C in my routing table, stands for connected, for 172.16.102.0 network. Wait, that's the wrong one. 101.0 network, and that needs to go out interface 1. So at that point, this router is going to want to send it out this interface to this host. So it's going to do an ARP request. If it doesn't already have the ARP entry in the ARP cache, it's going to send an ARP request for 101.2. This PC will reply, say, hey, here's my MAC address, and then this router is going to deliver it to that host. That is an example where we are connecting to two networks connected to the same router. The next example is going to be where we want to communicate out to something on the internet. So down here we have 172.16.100.2, we called it. It's going to make the same decision it made before. Hey, I want to go to this IP address that's out on the internet. We'll call it 9.10.11.12 again. I want to go to 9.10.11.12. It's going to check that IP address against its own IP address, subnet mask combination, and say, hey, that's not the same network I'm on. It's going to send it to the router. The router is going to pull the IP datagram out of the Ethernet frame. The router will examine the destination IP address. It will say, hey, that destination IP address is not me. Let me check my routing table. It will check its routing table, like 9.10.11.12. Nope, doesn't match that one. 9.10.11.12. Nope, doesn't match that one. 9.10.11.12. Nope, doesn't match that one. This final route down here is a static route. The all zeros route is referred to is how the default route is represented on a router. So it's going to say, hey, that 9.10.11.12 matches up to my default route. So I'm going to send it out interface 0. Crap, I screwed that up. Out interface 2. And that's a picture, so I can't even fix it. Crap, I have to fix that. Pretend like that says 2. Out interface 2 to a next hop of 172.16.102.2. So what that tells us is there's some router out here in this cloud with the IP address of 172.16.102.2, and we're going to be able to send our packets to that router, and that router will process them for us. So if the router knows where it needs to go to, connected route, it'll send it to those hosts. If it doesn't, it'll send it one hop closer to where it needs to go. It'll send it towards the final destination. We're assuming this router at 172.16.102.2 knows what to do with it. And it will also get it one step closer until it finally delivers it to some router that is connected to the network we need to send the traffic to. In that case, it'll be the 9.10.11 network. As I said earlier, we have a bunch of routers in the path across our internet, and each one of them will try to get one hop closer. So if we have this host, 172.16.100.10, wants to send traffic at 10.1.1.11, it's going to send to the first router. The first router will check its routing table and say, hey, 10.1.1.11, I need to send that to this router. And this router is going to send it to that router, and that router will send it to that router, and that router will send it to this router. And this router is actually connected to that network, so it will finally deliver it to the end host. Yeah, I think that's all I'm going to say about that. So how does IP make that happen? Well, the IP protocol defines the IP header. This is how the bits are laid out and what they mean, so that the receiving host and routers all are playing by the same rules, right? We have to know what the bits mean in order to interpret them and act properly. So the IP header looks like this. The header length can be between 20 and 60 bytes. The first 20 bytes are required. It can be no shorter than 20 bytes. 20 bytes gets us up to the destination address. We have some IP options we'll talk about a little later on that are not required, which is why they're called options. They can be from 0 to 40 bytes in length, giving us a total length of between 60 and 20 bytes, 20 and 60 bytes. The fields we have in the IP header, the version defines what version of the IP protocol we're using. We're currently using IPv4 and IPv6. We're talking about IPv4 today. This is what IPv4 header looks like. The header length defines how long the header is in 4-byte words. What the heck's a 4-byte word? Well, a 4-byte word is one of these lines, essentially, right? There's a byte, 2 bytes, 3 bytes, 4 bytes. So the header length defines how long the header is in 4-byte words. So we have 1, 2, 3, 4, 5. If we have 5 in there, then that means we have the minimum size header we could have. If we have anything higher than 5, then we have options. What's the highest value we could have in that field? Well, if we could have 60 bytes total length is the maximum, 5 will go into 60, what, like, I don't know, what's 5? What's 60 about 12? Is that right? I don't know. I don't know math. Yeah, I think it's 12, right? 5 times 10 is 50, and 5 times 2 is 10. That gives us 60. So yeah, so 12. So then that tells us that the maximum value we have in there is 12. However, when we look at these things, they're going to be written in hex. So the value you're actually going to see is going to be C for the maximum, I guess. Anyway, you can ignore that. I don't know why I told you that. Type of service, it can be used for quality of service. We're just going to ignore that for the most part. Total length, this is the total length of the datagram, including header and data. The ID field and the flags field and the offset field are used for fragmentation. We'll talk about those later. Time to live field, this is actually really a hop count. This tells us when we need to kill a packet. Why might we want to kill a packet? Well, if we have a routing loop, say our routing protocols are not behaving nicely and we get a loop in our inner network, this will kill the packet eventually. If there weren't some way to kill packets, if we got a loop, we would have packets circling around forever. And the only way to kill them would be to power off all the routers that were sending the packets around in a circle and then turn them back on. That's the only way. That'd be the only way to get rid of the packets. So time to live field, we set that when we send the packet, and then when it gets to 0, the router throws it out. Protocol field, this is similar to the type field we had in the Ethernet header. This tells IP protocol what upper layer protocol needs to get the data. This is how we know if this is TCP data or UDP data or ICMP data. This is how we know which upper layer protocol we need to give it to. Header checksum is something used for rudimentary error checking to make sure that the header did not change in transit. So for example, if something got corrupted and the IP address was supposed to, the destination address was supposed to be 192.168.1.2, but some bits got corrupted and the destination address actually showed up as 192.168.1.7, then the header checksum would detect that and we would throw out the discard the packet. Source address, that is who sent the packet. Destination address is who the packet is to. Options are optional. We'll talk about them later. Fragmentation. Talk about fragmentation. If we need to send data across a link that is smaller than the size of the packet, we might need to fragment it. What are some times you might want to do that? Well, PPOE has adds a PPP header on top of Ethernet. The PPP header is 8 bytes, so that makes our effective MTU 1492. So if our hosts are sending at 1500 bytes and we get to a link that's using PPOE, we can only send 1492 bytes. We might need to fragment those datagrams to get across. VPN is another example of something that might require fragmentation. If we're sending large Ethernet frames, 1500 byte frames, they get to a device that's doing VPN, well, you need to add some VPN header between actually, lots of times you add an entire new IP header and then a VPN header, and then you have your old IP header and your old data. Well, that's going to cause some problems, and that might cause fragmentation. So there's some reasons why you might have fragmentation. I said we would talk about these fields from the IP header later, the ID field, the flags field, and the offset field. The ID field is a value that is used to uniquely identify the datagram. We need that because if we break this datagram into 3 parts, we need to know which 3 parts all go together when they get to the final destination. So, for example, if the ID was 7 and I fragmented this packet, all of the fragments would get the number 7. We have some flags. The first flag, indicated by an X, is not used. The second flag, indicated by a D, is the don't fragment flag. If for some reason you do not want your packets fragmented, you can tell them to not be fragmented. You as a user will normally not do that. If you were writing an application that didn't deal well with fragmentation or you wanted to avoid fragmentation, you would probably be doing that at the application programming level. Not something you are going to normally see as a user. We'll see it in the lab because we're gonna we can give ping a command to tell it not to fragment. We'll see what happens. The M is used for the more fragments flag. That gets marked as a 1 if the packet gets fragmented, so we can know that more fragments are coming. And the offset tells where the data goes when reassembling the packet. So if we get 3 fragments sent, we need to know once we get them how they get put back together. A few rules about fragmentation. Packets can get fragmented more than once. Once it's fragmented, it will not get reassembled until it gets to the destination host. So if we think about a short link, a small MTU link in the middle of a network, the router on the other side of that link is not going to wait for those fragments and try to reassemble them. And no other routers are going to wait and try to reassemble them. 2 reasons for that. It doesn't make sense to reassemble them if they might get fragmented again later on. And then the second reason is IP datagrams are not transmitted in a manner that guarantees that they will all follow the same path. So it's not really feasible to wait for all the datagrams because each router in the middle might not see all the datagrams. The only one that's probably the only one that's going to get all the datagrams for sure is the final destination. So they'll be reassembled at the final destination. So here's a 20,000 foot view of what happens. We have our data with an IP header on it. We send it across a small link. It gets broken into two chunks. Each chunk gets its own IP header, and then they get delivered like they are independent datagrams. Here's a 5,000 foot view of it. I have ID 10 on my first datagram on the left. I have the flags fields of all 0, and I have the offset field of 0. It gets fragmented. My new IP header on my first fragment has a ID of 10. It has a more fragments bit set, and it has the offset of 0. That tells us it's the first fragment because more fragments is 1. It has been fragmented. Offset of 0 is the first fragment. If we look at my second frame, have the ID of 10 again. This time I have the more fragments set to 0. That means no more fragments are coming, and I have the offset set to 50. Why is the offset 50? Well, that's where the packet needs to go when it is being reassembled. That's where its data needs to go when it's being reassembled, and that is based on byte numbers. But you're saying it's 400 bytes, right? So this is from byte 0 to 799. If I break this up, this is from byte 0 to 399. So byte 400 is the first byte in this fragment. So what, I have a 50 there? Well, the way the fragmentation offset works is you divide whatever number you have by 8. So 8 will go into 400, and the answer will be 50. So the offset's 50. Why is it 50? Why do we divide by 8? Well, the fragment offset field is 13 bytes in length. The total length of an IP datagram can be is a 16 byte field. So we're missing 3, did I say 16 bytes? 16 bits in length. So we're missing 3 bits. So if we didn't, so 2 to the third is 8. So if we didn't use that factor of 8, we would not be able to fragment all possible IP datagrams because it'd be possible to send larger datagrams than we could represent in 13 bits. So that's why we divide by 8, because the offset field is 13 bits, the total length field is 16 bits. Here's another example. If we look at our IP header, now this time we have the don't fragment bit set to 1. So whereas before we fragmented that packet into 2 packets, that datagram into 2 datagrams, now we're not going to fragment. I drew that X to indicate we're not fragmenting it, and the router will send an ICMP error message back to the sending host. So some rules about fragmentation. If the packet is not If the packet is not fragmented, the more fragments field will have a 0 in it, and the offset field will have a 0 in it. If it is the first fragment, the more fragments field will have a 1 in it, and the offset field will have a 0 in it. If it is a middle fragment, the more fragments field will have a 1 in it, and the offset will have some number in it, right? Some non-zero value. And if it's the last fragment, the more fragments field will have a 0 in it, and the offset field will have a value in it, some non-zero value. So that's how you can determine which fragment it is based on the fields. Can we identify just looking at whether it has a number or not, which middle fragment it is? No, we would need to know the actual number of the offset to determine the actual order the fragments went in. So you can't just determine it because it has a number. But if you had all the offset values, you should be able to put it back together. Let's talk about IP options. Options may appear or not appear in the datagrams, which that was from the RFC. That's why they're called options, I guess. Some of the options you might see, if you look in Wireshark at the end of your IP header, you may see them. There's an end of option list that can be used to indicate options are over, and it also serves as padding. The no operation option, that can be used as padding. The options have to start on the side of the header. Let me go back up here and show you. So the options must start over here on the left side of the header. It can't start in the middle. So if you had an option up here that took up 2 bytes, right? You can't start your next option in the middle. So you put 2 bytes of no option, no operation to space that out. Record route. This is a way the IP protocol can be used to keep track of which routers that the packet goes through. There's only 40 bytes of space available, so that's usually not really enough space to keep track of the whole path. So it's not really used a lot. Lots of times if you want to know the route a packet is taking, you use the traceroute command to find that. Source routing, the next 2 options. Source routing is a way that you can specify in the IP options which routers you want your packets to go through, and then the routers try to honor that. Loose source route says, hey, I want my packets to go through these routers. You can also go through other routers, but you must go through these routers. And strict source route says, hey, I want my packets to go through these routers, and you can go through no other routers, only through these routers. Timestamp option can be used to keep track of the time when a router crosses when a packet crosses the other routers. So what about errors? I said earlier, there's no mechanism to augment end-to-end data reliability, flow control, sequencing, or other services. Well, if you want those things, you can use a transport layer protocol to get those things. For example, TCP will provide reliability, flow control, and sequencing. ICMP is used to report errors. So by using those other upper layer protocols, you accomplish those goals that are not built into IP. So you got any questions? Put them on the discussion board or bring them to class.